Okay, let's welcome you to the third functional class online. So last time we were looking at the set of bounded linear operators. So we are considering x and y, which are normed vector spaces, and we consider the set T, the set of linear operators T from x, y linear, such that T of x, the norm at y, is less or equal than k, the norm of x at x, for some k in 0 infinity. Okay, so this is the definition that T belongs to the bounded linear operators from x to y, which is contained in the linear operators from x to y. Okay, so the thing that we'll do, not in this class, but want to do further along, is we want to prove the following theorem. If x and y are Banach spaces, then B of xy, so the bounded linear operators from xy, is also a Banach space. Okay, so it's fairly intuitive in the sense that once we have completeness and norm of x and y, then we can start looking at the bounded linear operators going from x to a different to a space y, and we can actually check that under this structure B of xy is also a Banach space. Okay, so it has a norm and it's complete. Okay, so the first question, this theorem we won't prove now. The first question is, what is the norm? So what is the norm? So in a sense, following the notation we had before, we are going to consider, let me put the light here. We are going to consider, like from the theorem from last class, that we're going to say that the norm of T is going to be defined by the supremum of T of x norm at y, such that the norm of x in x is less or equal than 1. Okay, so what we saw from last class, from a lemma of the proposition last class, is that this is equal to the infimum over k, such that T x at y is less or equal than k x at x. Okay, so taking the infimum over the bounds here is the same as taking the supremum over the unit pole of T of x at y. Okay, and this is our definition. Let's call it definition. The norm of T is given by this. Okay, and what are we going to prove next? The lemma is that the norm of T, that this guy is a norm on Bx, y. Okay, so from the bounded linear operators to the other one. Okay, so what do we need to check? We need to check the axiom of a norm. So the first thing is that the norm of T is positive, and this is clear by definition. Okay, so we have positivity, and this is what I would say in this case is a good use of the word trivial. Now, let's look at something which is slightly more complicated, to say that if the norm is equal to 0, this implies T is equal to 0, where 0 is the operator. Okay, 0 is the operator. So let's put a 0 op. 0 is the operator. From 0 op goes from x to y, such that 0 operator of x is equal to 0 at y for every x in x. Okay, so this is the 0 in terms of operators. Okay, but if t is equal to 0, then t of x norm at y is less or equal than 0 times the norm of x at x, okay, where we are using this definition here. And this is actually equal to 0, which implies that t of x is equal to 0 at y for every x in x, okay, which is what we wanted to prove. Now, what is the third property? We need to check that if we take lambda t, okay, so what is the third property? We want to take the norm of lambda t, and we want to show that this is equal to the absolute value of lambda times the norm of t. In fact, okay, so first, just a reminder, lambda t applied at x is equal to lambda times t of x. Okay? So what can we see right away? So let's take x in the unit ball. Then lambda t x in norm is going to be equal to lambda, absolute value of lambda, times t of x. So then, if we take the supremum, over x in B1, this is going to be equal to lambda times the supremum of x in B1 of t of x, which is just the modulus of lambda times t. Okay, and now the final property is, let's say that we take s and t in the bounded linear functionals from x, linear transformation from x to y. Now, if we take the norm of s plus t applied at x, this is going to be less or equal by, okay, so this is equal to the norm of sx plus tx, which is less or equal now by the triangle inequality. By triangle inequality, this is less or equal than sx plus tx, which is also equal, less or equal than the norm of s plus the norm of t applied to x. Okay, so then in particular, this implies that the norm of s plus t is less or equal than s plus t. Okay, and this is the triangle inequality. This is the triangle inequality. Okay, so this finishes the proof for this specific example. Okay, so let's follow an observation that is in the book. So the observation is that if we consider the linear operator, which is going from Rn to Rm, that we define by t of x is equal to a times x, where a is an Rm by n. Okay, so this is a matrix. So then the norm of t is equal to the induced norm of the matrix, okay? So this is the induced norm of the matrix. So we could actually change the norms in Rn and Rm to get a different norm for A squared. But as for A2, we could have like A1 infinity. But as we have seen, for finite dimensions, all of these norms are equivalent. Okay, so what other example have we usually checked? We take f in the Banach space, which is given by the continuous functions of the 0, 1, and we take t of f, which is equal to f of 0. Okay, so what should we note is that t of f in norm, so here this is t is going from c0, 1, this is my x, and it's going to r, okay, and this is my y. So the norm at y is just the absolute value, so t of f is just the modulus of ff of 0, which what we have shown before that this is bounded, this is less or equal than the norm of f infinity. And in particular, if we take f of 0 to be, if we take f to be identically 1, so let's call it f tar, the norm of f tar infinity is 1, and t of f tar, the norm in the R, is just equal to 1. Okay, so in particular, what we have shown is that the supremum of f of the norm f in B1 of the norm of t of f is equal to exactly 1. Okay, this is because this is less or equal than, here you have a 1 times the norm in f infinity, and here if we take the f tar, which is exactly equal to 1, then we get that the t of f tar is equal exactly to 1. Okay, now next, what do I want to do? So the next thing we can talk about is what happens if we take a subset Wx, which is a linear subspace, which is dense. Okay, so we consider S in the bounded linear functions from W to Y, then exists, then for every S in the bounded linear functions from W to Y, there exists a unique T that goes from the bounded linear functions from X to Y, such that T is an extension. So T of W of omega is equal to S of omega for every omega in W. Moreover, the norm of T is equal to the norm of S. Okay, so let's look at a proof of this. So the first thing that we need to check is that we can extend S. Okay, so let's take two sequences. We consider two different sequences. Okay, so this is perhaps a little odd to draw because this is a more of an infinite dimension kind of thing. So we have X which is given by this space, and now we have W, which basically has sort of every direction. So it's dense in X. So now for every point in X, I can find a sequence of points in W that converges to X. But there might not be only one sequence, so there could be two different sequences. So for a given X in X, we could find, we can always find a sequence Xn, which is contained in W, such that Xn converges to X when n goes to infinity. But the problem is this sequence is not uniquely defined. Okay, so in particular, what we would like to do. So we would like to take S of xn, take the limit when n goes to infinity, I call this t of x. Okay, but we need to check now that if we have two different sequences, we still have the same limit. First of all, we need to check that there is a limit, and we need to check that the limits actually agree. So let's say that we consider xn that converges to x and yn that converges to x, such that xn and yn are subsets of W. So in particular, if we take, we want to check that Sxn and Syn converge, and Xn and Xyn converge, and that the limit when n goes to infinity of Sxn is equal to the limit when n goes to infinity of Syn. Okay, so what do we need to check to say that these guys converged? Is we need to check that Sxn or Xyn are Cauchy sequences. That's how you check that things have a limit. So what do? You take the norm of Sxn minus Sxm, and we want to show that this is small where n and m are big enough. So this is less or equal than the norm of S times the norm of Xn minus Xm. Okay, and this is because S is bounded from W to Y. Now, because Xn converges, then Xn minus Xm is small enough for n and m large, n comma m large. Okay, so this implies that there exists the limit when n goes to infinity of S of Xn and it exists the limit when n goes to infinity of s of yn. But next we want to actually check that these two limits are the same, so we can take s of xn minus s of yn, and we take the norm. But this, by using linearity, is the norm of s of xn minus yn, but by using the fact that s is a bounded linear operator, this is less or equal than the norm of s times xn minus yn, but this guy goes to 0 when n goes to infinity, because this goes to x and this goes to x. Okay, so we just shown that the limit of s xn is equal to the limit of s yn. Okay, so there's something, I guess, one of the assumptions here should be that y, so around here we are going to think that y is complete. Okay, so y is a complete Banach space, so you can actually do all of these things and actually get a limit. Okay, so this way we have shown that there exists a limit. So in this way we can unequivocally define the extension operator t. Okay, so morally, how do you find t? For every x in x, there is a sequence from w, and we define t of x as equal to the limit when n goes to infinity of s of xn, such that xn converges to x. Okay, so there is a couple of question is why is t linear and bounded? Okay, so how do we check that t is linear? So we take xn that converges to x and zn that converges to z. So in particular, this implies that xn plus zn, okay, so these two guys are in w for every n. So xn plus zn, this is also in w, converges to x plus z. So in particular, t of x plus z is equal to the limit when n goes to infinity of s of xn plus zn. But now using the linearity of s, this is equal to the limit when n goes to infinity of s of xn plus the limit when n goes to infinity of s of zeta n. But now this guy is just t of x, because this is a converging sequence to x, and this is t of z, because this is a converging sequence to z. So what we just proved is the linearity. So similarly, if xn converges to x, then lambda times xn converges to lambda times x. So we can show that t of lambda x is equal to lambda t of x by the linearity of s. Okay, what else do we want to do? So now the next thing is we want to check that the norm of t is equal to the norm of s. Let's see if I can find my notes. So the norm of t is equal to the norm of s. So what do we do? So clearly, so the supremum, or how do I put it? The ball of radius 1. So the set of w such that the norm of w is equal to 1. So the norm of omega in W such that the norm is equal to 1 is a subset of the set of x such that the norm x in x such that the norm of x is equal to 1. So in particular, this implies right away that the supremum the supremum over, let's call it B1W of S of omega is less or equal than the supremum over B1x of Tx in norm. Okay, but now we'll actually show that these two supremums are equal by saying, okay, so let's assume that this supremum is slightly bigger. So then you can find a point such that the norm of T of x is actually strictly bigger than the supremum. Okay, so if we can do this proof by contradiction, but the construction is more or less the same. So assume, let's consider, we consider x star such that norm of x star is equal, less or equal to 1, and T of x star is strictly bigger than the norm of S, which is equal to the supremum over B1W. Okay, but if this is the case, by the definition of T, there exists Xn, which is contained in W, such that Xn converges to X star, and to Xn converges to X star, and this is in X. So in particular, we have that the norm of Xn, and here we can take the norm of X star has to actually be equal to 1, because if you have you can actually show that the supremum will be attained at the boundary, because if it's attained inside, you can actually multiply by something which is larger than 1 and still get something larger. So you can actually show that the norm of the maximizer will be at the boundary. So in particular, what we have is that the norm of Xn converges to the norm of X star, which is equal to 1. So then what we can actually show is that if we take Wn, omega n, which is equal to Xn over the norm of Xn, this is actually in the ball of radius 1 of W. And what other property that we have? So using this property here, we have that Wn converges to X star. Okay? But in particular, by what we have shown before, we have that the limit when n goes to infinity of S of Wn, by the norm, this is less or equal than the norm of S, is equal to the limit when n goes to infinity of S of Xn, which is just equal to S, which is just equal to T of X star, which is, now we can take the norms of all of this. If we take the norms of all of this, this is the norm of T of X star, which is, by assumption here, the strictly bigger than the norm of S, and this here is a contradiction. Okay, you don't actually need to do this proof by contradiction, but For me, proofs by contradiction are slightly simpler. Okay, so this actually shows you that because you can take every norm, every point in the unit ball can be approximated um, by a sequence which is also in the unit ball, we can actually show that the norms have to coincide. Okay. What else do we want to say? So the next thing that we're going to look at for a bit is isometries. Okay, so this is something I had said before in class, but let's write a couple of definitions. So definition. So let's say that we have T, that is a linear transformation from spaces X and Y. So T is called an isometry if the norm of T of X at Y is equal to the norm of X at X for every X in X. Okay, so you have an isometry if the norm is equal for everything. So in particular, so let's look at an observation that's done in the book. So if we consider the identity, which is a linear operator from X to X, so the identity of X is just equal to X for every X in X, this is clearly an isometry. So the idea is that isometries are a generalization of the identity. So we can sometimes will need to understand some things that are equal up to a linear transformation are literally the same for us. Okay, so let's look at the following thing. So the definition is if T from if there exists a surjective isometry from X to Y, we say that X and Y are isometrically isomorphic. So, okay, so this is something that is pretty common in functional analysis. The idea is that once you can able to get an isometry from one to another, from one space to another, then understanding the space X or understanding the space Y is the same. They also actually have the same exact properties. So I should point out in this definition the word surjective. So in finite dimensions, so the observation is in finite dimensions, isometries need to be surjective. Well, actually, even that is not quite true. So, but anyways, yeah, don't necessarily call me on that one. But the point is that this surjectivity in infinite dimensions starts becoming a little more complicated in the following sense. So you can be injective without being surjective. Okay, so in finite dimensions, isometries of the same space need to be surjective. Okay, so what I'm trying to say, let's say that we take T from Rn to Rn, then if T is an isometry, then T is surjective. Okay, this is no longer true in the infinite dimensional case. So if you go from a Hilbert space into a Hilbert space, if T is an isometry, then it's not clear, then this does not imply that T is surjective. So morally, this is the fact that in infinite dimensions you can sort of always add an extra dimension and nothing really goes wrong. So what is the typical example of this? The typical example of this is T is a shift operator. So what is a shift operator? T goes from, let's say, little l2 of r to little l2 of r, which is given by T of the sequence x1, x2, infinite sequence is just going to be 0, x1, x2, and so on. So T is clearly an isometry. And T is not surjective. Okay, so this is a shift operator because morally what you're doing is you grab the sequence and you move it one to the right. So in particular, so we should notice, we can notice that T of En is equal to En plus 1. So you're shifting everything 1, 1. And you could shift by 1, or you can shift by more, shifting by k, by a finite k. And this will be a family of isometries which are not surjective. Okay, now, this is a theorem I had mentioned before, and this gives you, morally, this is a good segue into the following. So what is the theorem that we can prove here? So theorem, any infinite dimensional separable Hilbert space is isometrically isomorphic to little l2, and here we can put R or C depending if it's a real Hilbert space or a complex space. So what is the proof of this? Every separable Hilbert space admits a orthonormal countable basis En contained on H. Okay, so then what does this mean? Is that for every x in H, there exists alpha n in little l2 such that x is equal to the sum from with n in n of alpha n En. Moreover, by Bessel's, moreover, by Plancherel, we have that the norm of x in H squared is the sum from n in n of alpha n squared. Okay, so what is the clear isometry? So T of En, okay, so T is going from H to little L2. T of En is going to be equal to, let's call it E tilde N in this case, which is going to be 0 and zeros after that. Okay, and this is position N. Okay, so this is clear that T is an isometry. T is an isometry. T is an isometry by this property here. So in particular, what is the corollary of this? The corollary is that every separable Hilbert space is isometrically isomorphic to each other. Okay, so they're all the same. So understanding this space L2RC is the same as understanding every Hilbert space. So in particular, when people talk about Hilbert spaces, they just talk about little, like they just talk of a L2 space, because L2 is literally the only Hilbert space that there is. Okay, finally, I just wanted to do an exercise, being that we're in the exercise mood. So let's look at exercise 4.10. So let's take H a Hilbert space, and we consider a vector y in H, and we consider the linear operator Ty that is going from H to R. Okay, so this is a linear functional. Okay, this is what I usually call is a member of the dual. Okay, so T of y is what I'm going to be referring later on as H star. Okay, so this is the dual of H. Okay, so what we are going to show is that actually H star is a Hilbert space and H star is actually equals to H. Okay, so H star is actually isometrically isomorphic to H. But anyway, so let's start with the right thing is that T of y is in the bounded linear functionals from H to R, and the norm of T of y is just the norm of y in H. Okay, and this is the norm in the linear functions. Okay, so sorry, and I didn't say what T of y was. T of y applied to x is just the inner product with x and y. So how do we actually find the norm of this? This is by Cauchy-Schwarz. So if we take T of y of x norm in R, this is equal to the absolute value of x comma y, which is less or equal, and this is by Cauchy-Schwarz, to the norm of x times the norm of y. So in particular, we have that the norm of t, or ty, is less or equal than the norm of y. But now, okay, if y, okay, so if y is equal to 0, then t of y is identically 0, and we have that the norm of t of y is equal to the norm of y. Okay, so let's assume that if y is different from 0, then norm of y is different from 0. So in particular, we can consider y over the norm of y, which is in the unit ball. So if we take ty of y over norm of y, this is equal to the absolute value of y over the norm of y applied to y, which is just equal to the norm of y. So using the fact that the t of y is equal to the supremum over v1 of the norm of ty of x, this will be, in particular by using this case, bigger or equal than the norm of y, and we have shown before that this is less or equal than the norm of y. So in particular, this implies that t of y is equal to the norm of y. So one of the things I will show later on is that these are actually all the linear functionals going from H to R. So the dual of H is H itself. So morally, the dual of L2 is L2 itself, and this is where like Hölder's inequality or Cauchy-Schwarz inequality plays a role. So the only thing that we can do to get a functional from H to R, which is bounded, is by pairing against something which is already in the space. Okay.